Hello my dears. Listen a question. See, a question is given like say a simple transmission line it consists of the current I is equal to 1 per unit at a 0.8 power factor lag, and E angle delta is the sending end voltage, and V is equal to 1 angle 0 is the receiving end voltage. This is all in per unit quantity. XL is nothing but the transmission line reactance, which is nothing but 1.2 per unit. Determine first one active power output and steady state power limit, and B keeping the active power constant. If the excitation is reduced, find the critical excitation corresponding to operation at steady state stability limit, or simply stability limit. So let's discuss one by one, my dear. Let's discuss one by first question. First of all, we have to find active power output. Active power output. If it's given in terms of per unit quantity, it is very easy to find the active power output per unit. You can P per unit, that is the active power per unit is nothing but, my dear, V per unit into I per unit into cos phi. Simply V per unit into I per unit into cos phi will be the active power output. So V per unit is nothing but, my dear, 1, and I per unit is nothing but, my dear, 1, and cos phi is nothing but 0.8. So 0.8 per unit will be the active power output. That is nothing but P per unit. Okay. So for this question, the answer will be 0.8 per unit. And steady state power limit. This is sub and this is next. Steady state power limit, my dear, power limit. The steady state power limit is nothing but, my dear, P is equal to EV divided by X into sine del. EV divided by X into sine del. So what are the unknown here for finding X? X is given, right, 1.2 per unit, that is no problem. V is given 1 angle 0, that is also no problem. But E and sine del we don't know, right? Del we don't know, E also we don't know. How can we find that? See, my dear, there is a relationship, basic voltage relationship, KVL relationship we can write like E angle delta will be equal to E angle delta, that is the sending end voltage will be equal to the receiving end voltage, that is nothing but 1 angle 0 plus J into IXD. Am I right? The receiving end voltage plus the voltage drop across the transmission line will be the sending end voltage. Symbol mathematics, symbol KVL. So symbol nothing but 1 angle 0 plus J into I is nothing but, my dear, 1. So 1 into XD is nothing but, my dear, 1.2. So if you solve this, you will get, actually in real examination, in competitive examination, without using calculator, that this type of J terms will be simplified version, J1, or you can easily find the answer. I mean, okay, that's all. I mean, you can easily find the answer where you will get. But now it will be 1.95. It is a gate question actually, my dear. That's why. Gate you can use the calculator now. But take the concept, absorb the concept. So a simplified version without the calculator may be asked, so that you can easily ask. You can easily solve. So 1.97 angle 29.7. So what is the meaning? This 1.97 is nothing but, my dear, our E, and this is nothing but, my dear, our del. Simple. Okay. So from that E will be 1.97 and del will be 29.17. Simply you substitute 29, you can round it to 30 also. No, you can simply substitute. You will get the steady state power limit as P is equal to E. You got now 1.97. These all are in per unit. Okay, these all are in per unit because these all are in per unit now. So the answer is also per unit. So 1.97 into 1 divided by XD is nothing but, my dear, 1.2 into sine 29.17. If you substitute these, you will get the answer like, you will get 1.6.8. Okay, wait 1 minute. You have to find steady state power limit now. Steady state power limit means, really sorry my dear, Small correction, my dear, a small correction. We have to find steady state power limit. Limit means there will not be any sine delta term. Simply you have to find steady state power means you can give EV by x into sine del, because if they have specified power limit means it is operating at the steady state limit angle. Limit angle is nothing but del is equal to 90 degree. So sine 90 will be 1. Simply you can have EV divided by x only. So EV divided by x only you have to calculate. EV divided by x only you have to calculate, and the answer will be nothing but, my dear, 1.642 per unit. 1.642 per unit. So that is the what steady state power limit. So A section is over. Next one, B. B section, we can see keeping the active power constant, my dear. So active power constant means, which is nothing but, we already discussed that active power, how much you got active power as? Active power, how much you got? VI cos phi 0.8. Na? So 0.8 will be a constant. So same constant we have to maintain. So P will give 0.8 will be, you have to maintain. If the excitation you reduce it, find the critical excitation corresponding to operation at a stability limit again. So we have P is equal to what, my dear? EV divided by x. To stability limit means sine 90 will be equal to 1. Simple. So x is there, V is already there. We have to find E for P is equal to 0.8. That's all. The meaning of the question is that keeping the excitation power, keeping the active power constant. Active power is nothing but P, which is nothing but 0.8. So P should be 0.8, and what will be the excitation value, or how much excitation you can reduce, or the excitation value corresponding to the operation stability limit. Operating at stability limit means EV by x into sine 90. 90 will be 1. So simply EV by x is from this. E will be equal to what, my dear? 0.8 into x divided by, simply you can do like 0.8 into x divided by 190. So simply 0.8 into 1.2. So it will be nothing but, my dear, 0.96, am I right? 0.96. Okay, so you got the value of what? E now. So see the beauty. Initially E was 1.9 something now. In the expression you got 9 something. So we reduced that one from 1.9 to what? 0.96. If you have to make the 0.8 power, I mean the active power as 0.8 per unit, you have to reduce the what excitation by, or excitation to 0.96 from 1.94 something. So that was the conclusion. Is it clear, my dear? So that is the answer for the question number B. That is the answer for the question number B. So the new excitation value will be nothing but, my dear, you can take it. So new excitation will be equal to 0.96 per unit. These all are in per unit quantity. Is it clear, my dears? Is this clear? Okay.